Today we're going to write a simple program in assembly language and compare that to a version in C. Assembly language, is being a low-level language, can be very cryptic and hard to understand. So that's why we're going to compare that to the C version of the exact same thing. This program simply goes through an integer array and adds up all the numbers and then prints out the result. Now, this will demonstrate indexing a one-dimensional array in assembly language, which is very useful. So we're going to go step through this program. So we go to debug and we say step into. The program gets the C part gets compiled and the assembly language portion gets assembled in the machine language. So this first portion here, this int, this is an integer array, an array of 5 integers. In this case, we just chose 1, 2, 3, 4, 5, and that's our array that's going to get added up. Some value is a storage area for the result as we're adding all those values together. And this format is just a string that's used in C to print out the result. It's going to print out sum equals, and that's going to print the integer value after the equal sign, and then print a new line character. Now this int I, that's going to be used as a counter value for the C portion of the program only. So let's step through this portion. Now again, we can use Visual Studio here to add a watch. So we can see that some value, it's going to track some value, it's going to track I as well. So now the first time through, I gets set to 0, and some value is initially set to 0 up here. So first time through, it's going to add the value of num value. Now I is equal to 0 in this case, which is going to point to the first item in the array, and that happens to be equal to 1. So the first time through, some value starting out at 0, so 0 plus 1 is 1, so now some value is equal to 1. And the same thing happens as we go through here. It's going to add the 2, it's going to add the 3, it's going to add the 4, and now it adds the 5. And so now I, this time as we go through, is now going to be greater than 5, so that terminates, and it will then print out that value sum equals 15. So now let's look at the same version of that exact same algorithm in this case in assembly language, in inline assembly. So we've got our ASM assembly language note here that tells the compiler that that this is going to be assembly language instead of C. Sorry, that's a compiler directive. This is LEA, we load effective address. So we're loading the address of numval into the ESI register. ESI actually typically stands for that's extended source index. That's kind of a traditional way to use if you're trying to get something. A source value of something is typically indexed by the ESI, but you could use whatever register you'd like. Now, so let's get the value of ESI here. Note that we can say, so this is the pointer to the numval string of integers in memory, and that's this value. Now I can say copy that value. I can come over here, paste it into place, and then hit enter. And then you can see here, in fact, if we switch this over to 4-byte integers, which is what an int is. Int is a 4-byte integer. And you can see that here's the values. There's 1, 2, 3, 4, and 5. And then here's some other things in memory. We're only interested in these first 5. Now, now the next instruction here. So now we've got ESI loaded with a pointer to the first value, points to this number 1 in memory. And now we need to set up a loop counter, just like in the C program we had I as a loop counter. In the assembly language program, we're going to use the EBX register, and we're going to initialize that to 5, which that's what the move does. So now EBX is equal to 5 over here. And now we also need to initialize the what was in the C program. It was sumVal. We're going to use EAX instead to sum up all of these different values. So we need to initialize that to 0. And this label is the start of our loop here. So we're going to add into that EAX register. As we said, that's where we're going to accumulate our values. We're going to add the value of ESI. So as we had said, that ESI currently is 27FEB0, which is pointing to the number 1, the first element in the array. And we'll step through that. So EAX, the value of EAX is added to the value in memory pointed to by ESI is added to EAX, and it was initially 0, so we add 1 to it, we get a 1. Now the next thing we need to do is we're going to have to increment the pointer of ESI for the next go around to point to the next value in memory, which is 2 in this case. So since an integer is 4 bytes, we need to increment the ESI register by 4, and that's exactly what this instruction here does. Add ESI, 4. So we step through that, and you can see that over here ESI has been incremented by 4. And the next thing we need to do is change the loop counter. Again, just like in the C program up here, the loop counter, well, actually we're doing it a little bit differently in C. Typically in C you do an increment. In this case we're decrementing, and the reason for that is it makes it a lot simpler to write this code. This way we can just decrement the EBX value down to 0, and when the EBX hits 0, this jump non-zero will no longer jump, and that makes things a lot simpler. So okay, so we're decrementing the loop counter, and the EBX value is 4, and so jump non-zero. Now, if EBX had hit 0, then this wouldn't jump, but this is non-zero. Our flag here is non-zero, so 0 flag is false. So it's going to, because it's false, it's going to jump back up to our label 1. And same procedure is repeated. We add the current number in the array to the EAX register. And you know, as we said, this is changed to EB4 because the ESI register has been incremented by 4. As you can see, that points to the 2. And again, same thing all over. Decrement. We're incrementing the pointer again. We decrement the loop counter, and then we jump. Repeat. Rinse. Wash. Repeat. So now we've got to go through this one last time. It's now pointing to the 5. So we'll go through this last time. EBX is now 0. When you use this decrement instruction and it sets this value to 0, it sets the 0 flag. So now the jump non-zero is no longer true. So we go on to the next instruction. And this again is very similar to the way the C program works. Now we're taking this EAX value that we've accumulated with with 0f. 0f is equal to 15. 1 plus 2 plus 3 plus 4 plus 5 is equal to 15, just like in the C program. So now that value is saved, and then we use the C function printf to print that out, just like we did for the above C portion of the program. And as you can see here, now we have we've printed the sum equals 15 twice. So it shows that the assembly language version was produced the same identical result to the C program. But now we can look at the disassembly and actually compare these two different things. Now, skipped a little bit ahead here. Here is the C portion of the program. Now, the C portion of the program is right here. So you can see that the assembler has to do its own thing. The C program in this case is every time it's writing out to memory. So you know, for the whenever it does the summation, it actually writes that value out to memory. And that's actually a little bit less efficient. It's going to take longer. Writing to memory takes much longer than it does to write something to a register. So and also you can see that there's actually significantly more code associated with the C program. So we come down here, and of course this is pretty much identical to what's out there, but it does show you, does give you additional information as to how many bytes these individual instructions take up. And you can see, you know, if you were to subtract, let's see, so the size of this assembly language program would be this value, 003053EC, which basically this is the start of the next instruction after this. And here's the start. This is the start of the instruction. So if you were to take this value here and subtract this value, that's going to tell you exactly how many bytes we have. Or we can just count them. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We've got 24 bytes that's making up that program. I won't bore you by counting through this again, but there's definitely more instructions involved in this C program. It's a significant percentage more. And like I said, since we're writing out to memory, this is slower. So this is one of the advantages of assembly language, is you get a much more efficient program, and of course it's going to actually run much, much faster. Well, that's all we have for today.